Welcome to the week 6 tutorial. We're going to look this week at delay, looping, and recording. But before we do, I just want to introduce a couple of new objects. And, I'm trying to introduce the objects that you're going to see again and again very commonly in your work with Macs. So I'm still only introducing a relatively small set of objects, but I'm trying to introduce the most useful and the most expected objects. So another one that shows up all the time is the counter object. And counter just counts bangs or integers and reports how many there have been. And it takes an argument for the beginning of the count and the end of the count. So now it's going to count from 1 to 8 and then start over again. And we can change the direction of the count with a toggle. So setting a toggle into the second inlet will make it count down. We can also cause the counter to reset to a certain number the next time it's clicked. So I've sent 3 into the middle inlet. So when I click this button, my next count is 3, and then it keeps doing what it's doing. Switch it back to forwards counting, hit 3, and it'll go 3, 4, 5, 6, 7, 8, 1. And we can also change the maximum value of the counter. So if we want this to suddenly become a counter 12, now it's going to count up to 12. 1, 12, back to 1. And note that the argument of the counter doesn't change. So when we open up our patch, this will be a counter 1 to 8, and then afterwards we can change it to some other value. Now it's a counter 4. 1, 2, 3, 4, back to 1. This is standard in Max objects. The arguments you typed in to the object will not change, even if the object's state has been changed internally. You're not getting visual feedback on that, but it's purposeful in the sense that this gives us a default value or the starting value when the patch is opened. Metro to counter gives us a sequencer. If you want to be able to set your metronome rate in seconds, you can just use the times 1000 and type your seconds in here. So a half-second metronome, and every half-second it's just going to give me the next value. Double speed. And that's the fundamentals of sequencing there. And the other object I want to show is actually a pair of objects. The send object, and you give it an argument that's arbitrary. Let's call it my data. And then a corresponding receive object. And what this does is it creates a wireless connection. So anything I send into send my data comes out of any receive my data. Right? So I've wirelessly connected these number of boxes. Now it doesn't work backwards. The data doesn't flow back up the patch cord, but I can send to multiple receive locations, and I can have multiple send locations as well. So I can change this value from here, change the value from there. And then by changing the name And again, these names are arbitrary. All they need to do is match. Anything sent into a send BBB comes out of every receive BBB object. And so this is great when you've got stuff spread out across your patch. It's also great when you've got something that you want to send to multiple locations. So if I want the output of this counter to go to several different places, I can just use a send my count and then a receive my count anywhere else in my patch. And something else can be receiving this count in addition to the playlist. So this is very useful. It's going to show up all the time. And the other related object is just the send and receive tilde objects, which are for making wireless sound connections. So send tilde sound out and receive tilde sound out. Now my sound will be sent wirelessly out to the speakers from here to there. So also I just want to address a conceptual issue. A couple people have said, you know, I'm a sound person, so the image stuff is particularly challenging for me, or, oh, I'm an image person, so I don't really understand the sound stuff. And that's valid. That's, of course, true. You have a disciplinary background that is going to make one aspect of Max more easily grasped than another aspect of Max. But part of the goal here also is to learn Max as a language for interdisciplinary communication. So that's why I'm showing everything as image and sound, showing it in as many ways as I can while still being time efficient in the tutorials. And so it's important to really put in the additional effort to wrap your head around the concepts that are outside of your area of specialty or your area of expertise. Because a large part of what we're going to be using Max for is for you as a musician or a sound artist to receive an idea from a visual artist and be able to connect your work to that. It's not that you're necessarily going to create complex image-based work, but you are going to be collaborating with people who are using that portion of Max. So understanding how the structures work in both sound and image is really important, and it goes both ways. If you're an image person, it's really worth taking time and wrapping your head around the sound aspects for the same reason. And I'll show you one point of conceptual crossover that's maybe useful. A couple of you have said, well, you're talking about X and Y coordinates, and that really, as someone who works primarily in sound, that doesn't resonate with me. And again, totally understandable. And we do have those concepts in sound. We just use different terms for them. And when I think about the notion of horizontal motion in sound, we deal with it constantly. It's panning between the left and the right speaker. That's the X. It's exactly analogous to whether something's on the left side of the screen or the right side of the screen in an image context. And so, this notion of there being a left and a right in sound is very much the same thing that we mean when we're talking about X in image. So sometimes just understanding that difference in terminology is enough to be helpful. So here's a sound pan to the left. Here's a sound pan to the right. Or we could say this sound's X is -1. And it's exactly analogous to a jit.gl.layer. If we wanted to move the plane to the left, we'd move it x minus 1, and centered is 0. Now, you might say, okay, well, that's x, what's y? And, y could be any number of things, but, the y that we deal with all the time, and it's laid out this way on the screen most of the time when we're working with sound, is amplitude, it's volume. The y of the sound, the vertical position of this fader. Here we have x and y as applied to sound. So of course it doesn't translate exactly, but I think it translates enough that there's a conceptual linkage to be made there. All right, so let's encapsulate this stuff, and we'll move on with the main material for today. The nice thing about receive objects is they stay outside of the encapsulation, so the encapsulation has no chords, but it will still work. Note that everything resets when you encapsulate, so my counter resets back to its typed in arguments, counter 1 through 8. All right, so let's look at recording sound. We've seen the ezadc, which comes in as a microphone icon. We've seen the meter object, which just allows us to see the sound level coming in. We have the handy send tilde object, which allows us to send the sound coming in to multiple locations. And I'm going to introduce a new object, which is times tilde. It's multiplication. So it's the same multiplication that we saw here when we said 0.25 times 1,000 to convert from seconds into milliseconds. But here we're multiplying sound. What does that mean to multiply sound? It literally is another way of changing the volume. So if I multiply a sound by 0, it will silence the sound. Multiplying sound by 1 just allows the sound to pass through. Multiplying sound by 0.5 will be half volume. But in this case, it's a linear control of volume as opposed to the curved control of volume in the live.gain. So that's why we want to use it separately. And it has the added benefit of just being able to be used with a toggle as a sound on-off switch. So here we can see with another meter, when this toggle is set, my sound is on. When this toggle is unset, my sound is off. No sound is passing through. And I'm just going to take this and send it to mono out. And so you can see how this send and receive is already changing in an important way the way we're working in the patches. It's not going to be the mess of patch cables that it was, which is going to be important because we're going to start building things that are a lot more complicated. So if you turn this on, you will hear your live mic through the speaker. I'm not going to do that because of the way my recording is set up, but this is here for you to hear your live sound. And it's good to work in headphones because otherwise you're going to get a feedback loop in your room where the sound's coming out of your computer speakers and feeding right back into the microphone, which is close to the speakers if you're on a laptop. So this is an exercise best done in headphones. So what can we do with this sound? Well, we've already looked at one thing we can do with it, which is to analyze its volume and cause that to trigger things. Another thing we can do is process the sound itself. And the simplest thing to do with a sound is to delay it. And there's a number of ways to delay sound. We're going to use tapin and tap out. This is called a multi-tap delay. And this will create a 2-second delay. And this will create a 2-second delay on my voice. On my voice. And we can see that. And we can see that. And we can see that with a second VU meter. With a second VU meter. And of course, see that. And of course, see that. We're going to want a way to turn that sound off. And you heard that there was an error in the delay when I edited the sound portion of the patch while it was still running. And you're going to get that. I mean, Macs can be edited live. You don't have to stop the audio functionality to change things in the patch, but you do have to be careful about what audio objects you modify because you are going to get some unpredictable results. That said, it is entirely possible to live patch your audio. You just need to be pretty conversant with Macs in order to do it and not create audio artifacts. So what happened here? Well, tapin is the input to a delay line, what's called a delay line. And a delay line is just a continuous recording buffer in the computer that's recording the last 10 seconds of sound. And then we're tapping out of that at the 2-second mark. And this is based on the way tape delays functioned. A tape delay, which is the earliest form of electronic delay, was a loop of tape with the playhead in one location and the record head in another location. So the sound would be recorded onto the tape, and then as the tape loop spun around, that recorded sound would pass the playhead at some later point. And so a couple of nice things about this. You can have multiple tapouts, so multiple playheads on your tape loop. Hello. 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 So we hear, there's two delays now. There's two delays now. One at 2 seconds, one at 2 seconds, and one a quarter second later. And one a quarter second later. And you can create as many taps out of a delay as you want. And of course, these delay times can be modified. So now I have a 2-second delay. So now I have a 2-second delay. And now I have a 1-second delay. Now I have a 1-second delay. And now I have a quarter second. That is hard to speak. I have a quarter second. And now I have a 10 millisecond delay, which is a doubling effect. There's a 100 millisecond delay. So why do I bring up delay in the context of recording and looping? Well, because this is a recording. This is an ongoing recording of the last 10 seconds of sound. And this is sound from 2 seconds ago coming out of the tap out. So if I take that sound, 2 seconds delayed, and pass it back in, here we are with the feedback loop again, back into the tap-in, that's a loop. That's an audio loop. So I'll set this back to 2 seconds, turn on my delay, and capture it, and capture it, and capture it, and capture it. And when I turn this off, the feedback loop is broken. This is the same way in which we were using the G gate earlier. And also, with the floating point number box, the ability to have older sounds fade out over time. So if I put a value in here that's not 1, our toggle was setting this to 1, allowing all of the sound to pass back into the tap-in. If I set it to a value like 0.6, then only 60% of the volume of this sound is going to be passed back into the tap-in. So listen to what that does. 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 Right? It fades out over time. 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 New sounds are added at full volume. New sounds are added at full volume. But the old sounds are still there underneath. 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 Sounds are still there. Being reduced by 40%. 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 In each iteration of the loop. 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 So you've got a very powerful recorder right there. Now, the downside of this is that the recording only exists trapped in this delay loop. So there's not a lot of flexibility with that, but for live performance purposes, often this is perfectly sufficient for capturing live sound, looping the live sound, creating layers of captured live sound. But of course there are recording objects. And the recording objects are basically the same functionality that's built into the tapin, just broken out into several objects so that they're a bit more explicit. And those objects are the buffer, which has a name, arbitrary, sound 1, and a time, let's say 10 seconds. So what this has created is the same thing that's inside the tapin. It's a 10-second place for sounds to be recorded or imported. And we can record into the buffer with record tilde. And we're telling the record tilde we want to record into the buffer sound 1. So here we're going to receive our sound in. And record it. And I'll introduce a new object, which is the number tilde, which is going to allow us to see numbers represented as sound without using a snapshot object. This is number tilde. And to start recording, I send it a 1, and to stop recording, I send it a 0, and I can record up to 10 seconds. So I'm recording, and this is the percentage of the buffer that's been filled. And if I look inside the buffer, I see that's the recording I just made. And to play it back, there's a lot of objects for sound playback. The one I'm going to show you is groove tilde. And groove tilde takes a message to tell it where to start in milliseconds. So 0 means start at the beginning. If I didn't want to start at the beginning, I could start 1 second into my sound. But typically you'll start at the beginning. And it also takes one of these numbers as audio signal to determine the speed. And we're going to make a new object for that, sig1. Sig1 will typically play back at the speed at which the sound was recorded. I have a sample rate discrepancy, again, because of my setup for recording this tutorial. So when I play this sound, it's actually going to play pitched down. So I'm recording, and this is the percentage of the buffer that's been filled. So in my case, if I wanted the sound to play back properly, because I'm dealing with 2 different sampling rates in my audio equipment, I would have to play back at this odd speed. So I'm recording, and this is the percentage of the buffer that's been filled. But you shouldn't have that issue. You should be able to hear normal speed when your sound playback speed is set to 1. And Groove has a loop attribute. So I'm recording, and this is the percentage of the buffer that's been filled. So I'm recording, and this is the percentage of the buffer that's been filled. So I'm recording, and this is the percentage of the buffer that's been filled. And I can turn the sound off by sending a 0 to my sig tilde object, which will reduce the speed of the sound to 0. One other thing about groove tilde is we can set the loop start point and the loop end point in milliseconds here. So if we just wanted to loop from a half second in to a second and a half in, recording, and this is the 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 I'm recording, and this is the I'm recording, and this is so 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 I'm recording, and this is the 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 percent so I'm recording, and this is the percent so I'm recording, and this is the percentage so I'm recording, and this is the percent so I'm recording, and this is the percent so I'm recording. And the other thing you can do here is you can get quite short loops. You can even get sub-millisecond loops if you do floating point values. So I'm recording, 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 So rather than having a start and end of your loop, have a start and length of your loop. And you can achieve that by packing the two values together and adding them to create the length. And this is the percentage of the buffer So you have a whole range of sounds that can be explored there, and of course combining that then with a free manipulation of the speed, you've got quite a palette to work with. Etc. So it's one method of recording and one method of playing back sounds. If you want to save your sound to disk, you can write wave or write AIFF. Click that and it'll call up a standard save dialog to save your sound. And if you want to read a sound file into a buffer, use the import replace message, which will import the sound, replacing the current sound in the buffer and changing the buffer's length, importantly, to the length of the sound file that you're bringing in. Okay, so that's how this works with regard to sound. Let's take a look at the same concept in image. Just take all of my sound setup here So I'm recording, and this is the percentage of the buffer that's been filled. And you see that it played back the sound there because when I encapsulated, the 0 I had sent to this signal 1 was no longer sent, and it was sending 1 as the playback speed. So it's often something to note that your patch is going to change a little bit when you encapsulate it. So to capture video, we're going to use a jit.grab. We'll need a jit.world. And for jit.world, I'm going to do a couple of new things. I'm going to say at visible 0, because actually we don't need to see our floating window at all for this example. And then because we want to be specific about the frame rate, we're going to specify frames per second 25. 25 is an odd frame rate. 24 is a much more common frame rate, or 30 frames per second. 25 is nice because it's easy to do math in your head on. 1 second is 25, 2 seconds is 50, 3 seconds is 75, 4 seconds is 100. And it doesn't matter. We're not needing to line up this frame rate with any other piece of software or any other system, so we can pick an arbitrary frame rate, and 25 frames per second is going to look fine, and it's going to be easy to do mental math on. And if you're on a Macintosh, in order to have your frame rate be set, you have to turn off something called display link 0. I don't know why, I don't know what that is, but I do know that in order to specify a frame rate on Mac, you do need to turn off display link. So I'll have a toggle here to turn these on. I'll do a jit.p window. I have a square camera image, so I'm going to size it to 200 by 200. You can size it to whatever is in the same aspect ratio as the dimensions of your camera. And there's me. Hello. Hey, everybody. How you doing? And so I do want to talk about one other thing about jit.grab, because some of you are having difficulty managing your cameras. Just like we saw previously, there's a way you can generate a menu of all of your camera devices. It's a little bit convoluted, but I'll just step through it quickly right now. It's the message getvdevlist. And this stands for Get Video Device List. And when I do that, it will send out the video devices out the right outlet of my grab. So I can see here's my VDev list, is FaceTime HD camera, NDI video, USB camera, John's phone. And we're going to need to do a little processing on that list to get it into a menu. First of all, it begins with the word VDev list, so we can route VDev list. And then I'm going to use an object called iter, which is very much like unpack. It takes a list, and instead of spitting it out to different outlets, it spits the elements of the list out in order. Then we're going to use prepend append, and prepend is an object that puts a word in front of whatever's coming in. So here we're putting the word append in front of the elements in the list, and that's going to format them for a umenu. And we can use this umenu to set the V device. So get the list, it populates the menu, and then I can choose my phone camera, choose my other webcam that's up there, or choose my built-in webcam. And the one other thing you're going to want to do here is just add a clear message so that this will clear the menu and reload it every time we hit the VDev list, instead of appending more and more things on the end of that. So that's useful. You probably want to just like keep this and, you know, encapsulate it you'll probably just always want to stick that onto your jit.grab. And one thing I will show you is if there's something that you are going to like reuse, an element that you're going to keep coming back to, you can highlight it and just save it as a snippet here under some name that you're going to remember, vdevlist maker, and now that's saved. And when you go here to your snippets, you can search for it. There it is, and drag it in. So that's a great way to like put little components that you're going to use over and over again in an easy to access place. You save them down here with the paperclip plus icon, and you recall them here with the paperclip icon. All right, so let's record this video. So that's the jit.matrixset object. This is the equivalent of the buffer that we just learned with sound. The matrix set is a buffer for images. We put in the number of frames that we want. 100 frames would be 4 seconds. And then we specify the matrix dimensions. 4 planes, red, green, blue, and alpha. Char type data, data that is integers between 0 and 255, standard way of representing color in the computer. And then the dimensions of your camera. Mine is 50 and 52 by 50 and 52. You put in your camera dimensions there. So that's our equivalent of a video buffer. And now we need to write images into the buffer. Well, in order to do that, we're going to take every frame and send a bang on every frame. So 25 frames per second. I'm going to use our new object, the counter, to decide which frame of the buffer we're going to record into, frames 0 through 99. I'm going to use the third inlet to create a way to reset that counter to 0. And then I'll use the attribute of the matrix set index. The index is which matrix, which frame is the incoming video going to be recorded into, and then we'll just send the video in there. And so what happens is every frame for 99 frames, it will record that frame into the matrix set. And it's going to loop that recording. It's just going to keep recording. You can see there it's recording video frames. And to get a frame out, we send the message output matrix. And then the frame number. So if I want to see frame 50, there it is. If I want to see frame 88, there it is. If I want to see frame 2, there it is. And of course, what frame 2 is going to change the next time frame 2 is recorded. So if I output frame 2 again, I get a different frame. Let it record this. And now, when I output frame 2 again, I can use a button for this, I will see the most recently recorded frame 2. And again, we can automate this as well. If I want to play back the entire contents of this recording, I can use the same architecture here. To play it back. And so I can record some gesture and then stop the recording. And now that gesture is in the matrix set. There's a loop of that video that's been recorded. Now, of course, that's just the starting point. That's a very, very simple example, simple approach to this. So just to give you an example of something that's a little bit more interesting usage, take something like my function. We know the domain of a function, the default domain is 1000. And put in some sort of playback shape. It's going to play forwards, then backwards, then forwards, then backwards. It's going to play quickly here. It's going to play slowly there. And here we're getting a floating point number between 0 and 1. So this is simply a matter of scale 0 to 1, 0 to 99. And here I'm using scale with no floating point arguments because I actually want an integer output. My frame number is an integer. So we'll still accept a floating point input, but it's going to give me an integer output. It's not going to try to access frame 55.2. It's going to give me frame 55. So I'll turn off this playback and turn on this playback. And now we're seeing the playback controlled by this shape. If I wanted to play through this faster, I could just count to 500 and multiply it by 2. That's going to be double speed. One more approach to this that we'll look at quickly would be to use our line object and have it play between random points in the recording. So generate a new random point every second. And of course I can re-record my video at any point. One other thing you might want to add to this, and of course you should add many, many more things to this and really dig into it and explore it if this is an area that interests you, but we might want this recording to stop when it records all 99 frames. And that's a very simple use of our logic object. When the counter reaches 99, 99 is no longer less than 99 because it's equal to 99, so that turns off our G-gate. So I reset the counter to 0, it records 99 frames, and then it stops all on its own after frame 99, and it's recorded that bit of video while it's simultaneously playing it back here, ramping between random points. And you're probably seeing this as getting quite messy again, but now that we have the send and receive objects, that makes it really easy to tidy up. We can just do a send, and S is the abbreviation for send because you use it so often. Frame, bang. Take this frame bang and just send it to S frame bang, and then we can do, as you might expect, an R for receive frame bang. And this gets rid of all of these cables that are crisscrossing our workspace. And so finally, how do we record this stuff to disk? Well, we can read and write the jit.matrixset, but it's not going to write it as a video file. It's going to write it as a proprietary max file that's used for saving matrix sets. So if we want to actually record the video, we have jit.record at realtime1. Pass the video you want to record into there. This is going to record my live camera to a file called rec.move in the same folder as my patch. And then when I stop it, it'll close that file on the disk, and it's saved into the same folder as the patch. If you want to record with sound, that's jit.vcr. And the video goes in the right inlet, and the sound goes in the first two inlets, so I can look back at it's receive sound in. So, receive sound in. That should be getting my live sound input, and it is. And I'll just pass that sound into the first two inlets of the jit.vcr and record the file, testing 1, 2, 3, 4, 5, and open up the file, record the file, testing 1, 2, 3, 4, 5, and that's my live video recorded. And of course you could record the output of the matrix set as well. All right, great. That's some recording, that's some looping, and I think those are going to be really useful tools for you.